Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about development of surfaces of solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now, today's discussion will be about the development of a truncated cone, and this development will be carried out using the principles of the Radial Line Development Method. Now here, first of all go through the statement. A cone with base 54 millimeter diameter and axis height 72 millimeter rests with its base on the horizontal plane. A sectional plane perpendicular to horizontal plane and inclined at an angle of 25 degree to vertical plane cuts the cone at a distance of 15 millimeter from the axis. So here you see we have got a cutting plane is there which is at a distance of 15 millimeter away from the axis, and this is parallel to the axis. So if a cone is cut by a cutting plane which happens to be parallel to the axis of the cone, then the resultant shape of the cut section which will be obtained will be that of a rectangular hyperbola over there. So we are required to work out the sectional front view and develop the lateral surface of the remaining portion of the cone over there. Now let us start working out the projections of the cone, and then we will see how does the cutting plane cut this particular cone. So step 1, you draw the XY reference line. Now the top view of this cone will be a circle, that is circle will be representing the top view which will be drawn onto the horizontal plane, and this will be drawn below the XY reference line. Now the diameter of the circle we have picked up as 54 millimeter, and we are going to divide the circle or the cone into 12 equal parts, so that every sector will be there which is equal to 30 degree angle, right? So let us mark the axis points. So O and O1, they are the axis point, where O is the axis point at the apex, O1 it is the axis point at the base over there, right? Now let's mark all the 12 points. So we have marked the 12 points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 corresponding to the 12 sectors over there. Now having drawn the top view, now we are going to draw the front view. In order to draw the front view, we require how much is the height. So this is my axis point. So from O and O1 I am going to draw the axis line over there. Now this is my axis line, and projectors through all the 12 points of the base, they have been drawn onto the vertical plane. That is, since the cone is resting on its base, so all the points of the base, they will be lying on the XY reference line, right? So the front view of all the points, they will be available over here. Now once the axis is known, I can mark the axis point. So the axis is equal to 72 millimeter. So I get the point of the apex over there. So having obtained the apex point, so I can join all the slant generators of this particular cone over there. Next I mark the base points. So these are the front view projections of all the 12 points of the base which are drawn onto the horizontal plane over there or onto the XY reference line. Now this is my axis point at the apex. Then I have got the axis point which is lying at the base. So this is going to be the axis O dash and O1 dash over there, right? Now let us see, this is the projection of the uncut cone in the front view. These are the projections of the uncut cone in the top view. Now let us see how does this cutting plane which is inclined with respect to at VP at an angle of 45 or at an angle of 25 degree, right? So that there is a sectional plane which is perpendicular to HP and inclined to VP at an angle of 25 degree. So what's the name of this plane? The name of this plane is auxiliary vertical plane. So we call it AVP. So an AVP which is going to pass through this particular cone at a distance of 15 millimeter from the axis. So there is a cutting plane which is perpendicular to HP and inclined to HP at an angle of 25 degree. So let's draw this cutting plane. So this is the cutting plane which has intersected with the cone, and it has resulted in obtaining point of intersection 1, point of intersection 2, point of intersection 3, point of intersection 4, point of intersection 5, and point of intersection 6. So the cutting of the cone with this auxiliary vertical plane which is at a distance of 15 millimeter from the axis, and it is inclined at an angle of 25 degree with respect to the vertical plane. So this has resulted in obtaining 6 points of intersection. So the first point of intersection, it lies on the point 7. Point 7 means on the slant generator O7 over there. So the cutting plane is going to cut the slant generator O7 at the point 7. Similarly, the second point of intersection lies on the intersection of the cutting plane with the slant generator or the slant H O6. The third POI will be the POI of intersection between cutting plane and the slant H O5. Similarly, the fourth cutting point will be obtained between the cutting plane and the slant generator O4. Fifth one, it is the intersection of the cutting plane with the slant H, that is O3. And finally, the cutting plane also passes through point on a base, that is this point, which lies between the portion of the sector that is 2 to 3. So this was the sector. So between this sector, this is the point where it is going to intersect the base over there. So the 6 points of intersection, they have been obtained. Now we are going to mark all these 6 points in the top view, and all these 6 points, they will be drawn in the front view so that we can obtain the sectional front view of this truncated cone. So let us work that out. So point number 1, point number 1 lies on point 7, that is on the slant generator O7. At the point 7, I have been able to obtain the first point, point A. So this is by point A. So where does it lie? It lies on point 7. That is bottom of the slant generator O7 gives me point A, right? So this is the first point of intersection. Now I will be drawing vertical projector through this point A. Wherever this vertical projector is going to meet in the front view, point 7 dash. So this is going to give me the point of intersection A dash location in the front view. So just see, I have drawn, please check, I have drawn a vertical projector through A so that wherever it intersects with O dash 7 dash, so it intersects with O dash 7 dash at the point 7 dash over there. So I have been able to obtain point A dash, which is going to coincide with point 7 dash over here. So this is my first point of intersection. Now let me work out the second point of intersection. So second point of intersection of the cutting plane lies with the slant generator, that is O6. So name of this point is B, right? So this was small a, so this is small b. Now point B, it happens to lie on the slant generator O6. Now from B, I am going to draw a vertical projector up till this vertical projector meets in the front view the slant generator O-6 dash. This is my slant generator front view, that is O-6 dash. So wherever this vertical generator intersects with this slant generator, so I obtain the second point of intersection in the front view. So name of this point in the top view was B. So this point name in the front view will be B dash. So again point B lies on O6, right? And B dash also lies on O-6 dash. And B dash and B, they lie in one vertical line. Now the third point of intersection, it is there on the slant edge O5. So point C was obtained by virtue of intersection of the slant edge O5 by the cutting plane, which happens to be AVP. Now having located the C point, now once again I will be drawing a vertical projector upwards till it intersects the slant edge O dash 5 dash, right? So this is my slant edge O dash 5 dash. So wherever the vertical projector through C, it is projected upwards, and wherever it intersects with this O dash 5 dash front view slant projector, I obtain the point C dash over here. So this is my point C dash. So A dash has been located on the XY reference line, B dash has been located on the slant generator O dash 6 dash, and C dash point has been located on the generator O dash 5 dash. Now the next point is point D. So where does point D lie? Point D lies on the slant generator O4. You see, point D lies on slant generator O4. Now let me take point D upwards. As I am going to take this vertical projector through this point D, I need to work out its point of intersection with the generator O dash 4 dash in the front view. But you see, I am not able to obtain any point because I am looking from 90-degree angle over here. I am looking parallel to the axis line at this particular point. So now I will be using this simple fundamental. Whatever is going to be the radius over here, corresponding to that radius, I will be locating out the height of cutting point D dash in the front view. So simple relationship I am going to again explain. If the radius is small, please see the height at which this cutting plane will be cutting this generator will be high. If the radius is higher, then the height at which it will be the cutting plane will be cutting this cone will be lower. If the radius is still very high, then what will happen? The height at which POI will be obtained by virtue of cutting of the slant generator O dash 4 dash, it will be lower over there. So lesser the radius, more will be the height, more the radius, lesser will be the height. So here you see, I know the radius over here. Why I am not able to get the height? Because I am looking from the same side. If I am looking from the side, so that my radius is basically getting nullified, because my axis line and this point, they are going to overlap with each other. So what I am going to do, I am not able to see the radius over here. So what I am going to do, I am now going to look from the 90-degree angle. If I look at the solid from 90-degree angle, what's going to happen? I am going to rotate this radius. You see, this is my radius. I am going to rotate this radius onto the edge O1, which happens to be true length. You see, O dash 1 dash happens to be true length. So I have transferred it onto the true length, that is top view of the slant generator, which is representing the true length over here. So once I draw this arc, so the new point is located, that is D1. So this was point D. Once I rotated 90 degree, so it means that now I am going to look from this side. The moment I am going to look from this side, you see, I am able to have the feel of the radius. So this radius has been transferred over here. So once I know the radius, now I know the relationship, lesser the radius, more the height, more the radius, lesser the height. So once you see, I have this radius available with me. What is this radius? This is the radius at which my cutting plane is going to intersect with the slant generator O4. So I get this radius of point of intersection. So once this radius of point of intersection is obtained, now I am going to rotate it just like as if I am looking from 90-degree angle. So once you see, if I look at it 90 degree, I get the feel of the radius over here. So this radius I have to transfer it over here. So what I am going to do, I have just transferred this radius so that point D1 can be plotted on the slant generator, which is corresponding to O-1- in the front view. Just see, I have drawn a projector from D1 in the front view to intersect with the slant generator O-1-. This is my slant generator over here, right? So wherever this vertical generator which is drawn through this radius corresponding to this radius which was equal to this one, so OD is equal to OD1, and once I take this, you see, vertical projector upward, now wherever it intersects on O-1 dash, why I am allowing it to intersect with O-1 dash? Because I had transferred this radius onto the slant generator O1 in the top view. So D1 was the point which was lying on slant generator top view over there, O1. Now once I transfer it to the front view, I know the height. That is, this is going to be my height. So once I know the height, now this height I am going to transfer it onto O-4 dash. So once I transfer it back onto O-4 dash, I obtain the fourth point of intersection in the front view. So A dash, B dash, C dash, D dash. So these are the 4 points which have been obtained. Now the fifth point is point E. So point E, it is the point of intersection of the cutting plane with the slant generator O3. So D point was there, then you have the point E. Now E point happens to lie on the slant generator O3. Now from E, I will be once again drawing a vertical, you see, projector line so that it intersects with the front view of the same generator, same slant edge, that is O-3 dash. You see, this is my slant generator O-3 dash. So wherever this is intersected, I am going to get the point E over here. This is O dash and 3 dash over here. Just check, this is O dash 3 dash. So wherever this is intersected by a, you see, vertical projector which is coming through point E, and E was the point of intersection of cutting plane with slant generator O3. Now I have to show this point in the front view. So once I bring this upward, I locate this point E dash over here. So fifth point also has been located in the front view. Now the last point lies on the base. So cutting plane is going to cut the base between these 2 points, 2 and 3 of this particular sector. So point F is located over here. Now I am going to bring this point upward. Where? Now it is not cutting any slant generator, it is cutting the base. So base between 2 dash and 3 dash. So this is 2 dash, this is 3 dash point projection on the base. So between 2 dash and 3 dash, so this point will be obtained. So name of this point is F dash. So now you see all the 6 points, they have been located. Now I am going to join this with the help of a freehand curve. And once I obtain a freehand curve, this is the front view of the rectangular hyperbola, right? So this is the rectangular hyperbola, but since is it the true shape? No, this is not the true shape. Why? Because my rectangular hyperbola which is being obtained over here, this surface of the cut section happens to be inclined to the vertical plane. So there will be certain amount of foreshortening or reduction of the shape of this particular rectangular hyperbola. So this will be a smaller surface which will not be a perfect rectangular hyperbola as well. Now once we have obtained the surface, now I am going to do the shading, and this is going to be the sectioned front view, right? Now I am going to join the remaining portion of the solid. So please see, the remaining portion of the solid we are going to get. But before that, you see, one thing more is there. The moment you see I have joined this, I have worked out that now even the development has to be worked out. So in order to work out the development, I have found that total 6 points were there which have been projected in the front view. Out of these 6, this point and this point, since they are lying on the base, there is no problem regarding this. Why? Because I know the true length. The true length of the slant edge happens to be O-1 dash, and it happens to be O-7 dash over here. Why O-1 dash and O-7 dash? Why they are the true lengths of the slant edge? Because please check, O1 and O7, both of these points, O1 and O7, they happen to be parallel to the XY reference line, or they happen to be parallel to the vertical plane. So their projections, that is O dash 1 dash and O dash 7 dash, these projections once you obtain in the front view, these are the true lengths of the slant edges over there. But this does not apply to the remainder 5, you see, pairs of edges which are lying in between. So there are total 12 points we had assumed. So these generators, that is O dash 2 dash, O dash 12 dash, O dash 3 dash, O dash 11 dash, O dash 4 dash, O dash 10 dash, O dash 5 dash, O dash 9 dash, O dash 6 dash and O dash 8 dash. So these slant generators, that is these 10, you see, slant generators, they are not the true length. Why? Because their top view projection and front view projections both happen to be inclined to the XY reference line. So any points which are obtained on these slant generators which are corresponding to these 10 points, you see, these are the 10 points. So any of the, you see, points of intersection which are obtained on these slant generators, they are not going to be giving you the true length of the point of intersection. They will be providing you with the apparent length of the points of intersection over there. So what we need to do, from every point of intersection which is lying on these slant edges, that is, you can see O dash B dash, it lies on the slant edge, you see, O6, O dash C dash, this is again a point or the radius of the point of intersection, and C dash is going to lie on, C point lies on O5. Similarly, D lies on O4 and E lies on O3. So these are the 4 points. If I measure these radii, that is O dash B dash, O dash C dash, O dash D dash and O dash E dash, I am not going to get the true development of the surface over here. So in order to make an appropriate development, what needs to be done? From these 4 points, B dash, C dash, D dash and E dash, I will be drawing the horizontal lines so that wherever these points, they intersect with the true length over here, so I will be able to obtain the true length of this radius distance of this point of intersection C from the point O. So the true length name is given as C1 dash. Similarly, for D point, also once again I draw the horizontal line. So wherever this horizontal line from D dash, it intersects with the true length O dash 1 dash. So this point gives me the location of the point D1 dash. So D1 dash means it is the true distance of the point of intersection from the apex O dash over here. So I am going to ignore this distance. I have to use these distances over there. Similarly for point B, so this distance I cannot use in order to make the development over there. So for making the development, I need to draw a horizontal point line so that this point can be transferred onto the true length over there. The moment this B dash point is transferred over here on the true length, so this distance I will be measuring in order to show the development corresponding to the point B over there. So the name of this point, since this is true length and it has been obtained, it has been projected, so the name will be B1 dash. And finally the 4th point, E1 dash. You draw a horizontal projector through point E dash, wherever this horizontal projector is going to intersect with the true length, so this point radius will be E1 dash. And instead of measuring this distance of O dash E dash, so wherever required, I will be marking the distance of O dash E1 dash instead of O dash E dash, because these distances, they are the apparent length distances of the points of intersection from the apex point O, right? So we have worked out all the 4 points which were lying on the apparent lengths and their actual radii of the POIs, they have been evaluated over here. Now you see, I am going to join the remainder solid. So this is my total solid, but this portion has been cut. So you see, I have rubbed this off. Okay, so I have just hidden this portion. So this is the remainder solid which is left after the cutting has been done. So that is the reason you see I did not mark A, B, C, D, F points over here. So had I marked these points over here, so once you do the hiding process over there. That is, once you try to show the cutting of this cone, right, by an AVP, so these points would have been hidden over there. Now in the front view, the two extreme true lengths I am going to join, because these two slant edges, slant generators, they are going to show me the boundary of the cone. So these are the slant generators which are going to show me the boundary, and I did not join these slant edges because these were basically the artificial slant edges which are not part of the construction otherwise. So had it been a pyramid or had it been a prism, I needed to join all these points. Had it been a pyramid, I needed to join all the remaining portion of the uncut solid over there. But since these generators are only required to locate, to facilitate location of the points B dash, C dash, D dash and D dash, so these are not to be joined dark over there, right? Now let me draw the development of this particular solid or the cone. You see, this is my slant edge O dash 7 dash and O dash A dash, which happens to be true length. Reason? Because O1 and O7, they happen to be parallel to XY or parallel to the vertical plane. So the projections of O1 and O7 in the front view, that is on the vertical plane, they will provide me with the true length of the generator over there, that is O1 and O7 over here. So both are equal. So I am going to pick up this radius. So the radius of the curve is going to be O dash 7 dash, which is slant length, that is true length of the slant generator over here. This is my slant generator. So having obtained this apex point, now the curve has been drawn and 12 equal sectors they have been obtained. You see, once again this is an approximate method because we are not able to measure the arc length, rather we are able to measure the chord length over here. So since the shortest distance between 2 points 1 and 2 has been measured, so it becomes little bit an approximate method. So let me mark all these points. So since all these sectors they will be equal, so we have started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 1. So whatever is your starting point should be your end point. So I have started from point 1, move along till you reach point 1, till you reach back at this point. So the cutting will be done over here at point 1. So this is the development of the uncut cone over there. So had there been no cutting, no truncation, so this would have given us the development of a cone. Now since the cutting has been done, now you see I need to work out the locations of all these points onto the unfolded portion of the development over there. So let me work out point A. Where was point A lying? Point A was lying on the base and it was coinciding with the point 7 dash. So please see, point A has been located at the base and it is coinciding with the point 7 over here. So on the generator, on the slant generator O7, at the base point A has been located. Point B, please check. Point B, where does it lie? It lies on the slant generator O6. Please check. It lies on the slant generator which is O6. How much is the distance of this point of intersection from the apex? This is the one. Is this true distance? My answer is no. This is not a true distance or the true radial distance. Why? Because it is lying on the apparent length. Since it is lying on the apparent length, so this is also the apparent radius. So what I have to do? From B dash, draw a horizontal line onto the true length, either here or even here. You could have just transfer it here because this is also true length. So once you transfer it here, now instead of measuring the distance O dash B dash, now the true length has been obtained, B1 dash. So 1 means true length. So once I obtain this point over here, measure the distance O dash B1 dash over here. So once you measure this distance, so this distance will be marked over here onto O6. And where does point F lie? F lies between 2 and 3. Please check. Point F lies between 2 and 3. How do we locate this distance? Please check. I will have to move on to plan. Once I move to plan, this was the sector 2 to 3. I am going to measure the linear distance between 2 and F. Measure linear distance from 2 towards 3, and this will be the distance 2 to F. So using divider or using compass, I will be measuring this distance. So from 2, measure this distance along the arc which is going from point 2 to point 3. So point F is also located on the base. A is located, F is located. Now next, I have already told you B1 dash. So B1 dash lies on O dash 1 dash over there because this is true length. But where does point 1 lie? Point B lies. So point B lies on O dash 6 dash. So this was the apparent distance. True distance has been obtained over here. So I will be measuring this distance O dash B1 dash. So this has to be marked on the slant edge O6. Why? Because point B was lying on the slant edge O dash 6 dash over here. Next, my point is third point of intersection C dash. So C dash lies where? C dash lies on the slant edge O dash 5 dash. You see, O dash 5 dash. But this was apparent radius. So I have worked out the true radius by transferring this point onto true length. So this is my true length distance for the point C. So I need to ignore this distance. I need to use this distance. So I'll be measuring the distance of O dash C1 dash over here, and where I need to mark it on the segment or on the slant edge O5. So point C has also been marked. Now point D. So point D lies on O dash 4 dash over here. O dash 4 dash. But again, this radius can I use? No, I can't use. So why? Because this is an apparent radius. Transfer it to true length, I get true radius O dash D1 dash. So I have to use this radius where? On the slant edge O4. So on the slant edge O4, where does it lie? O4. So this is my slant edge O4. So measuring this distance O dash D1 dash. So I am going to plot it over here. This is my OD1. OD1. Distance is equal to O dash D1 dash over here. Last point E dash. So E dash lies where? E dash lies on O dash and 3 dash. Just see. E dash lies on O dash 3 dash. Let me measure this distance. O dash E dash. Is it the appropriate distance? No, because it lies on the apparent length. So once again, transfer it onto true length. Measure this distance. O dash E1 dash. You measure the distance O dash E1 dash. And I need to mark it where? On the slant generator O3. This is my slant generator O3. Onto this generator, point E1 will be marked. So E1 has been marked. Just check B1, C1, D1 and E1. They are evaluated true lengths onto the true length of the slant generator. Right? So all the 6 points, they have been obtained. Once I join, this is my true shape of the rectangular hyperbola. You can see the symmetry over there. This is the true shape of the rectangular hyperbola. So this portion has been removed. Now let me join the remainder portion. So once I join the remainder portion, I am able to obtain the true development of this particular cone as it is appearing to me, right? So this way, by using the principles of the projections of the solid, the section of the solid and the development, I am able to work out the section front view, the section top view, and I am also able to work out the development of the lateral surface of this particular truncated solid over there, right? So this is all for today. So we'll be continuing with few more cases of development of surfaces of solids in our forthcoming lecture discussions over there. So thank you very much. Thanks a lot. Thank you.